Section 5.3, Complex Zeros and the Fundamental Theorem of Algebra. In Section 5.2, we learned how to find the real zeros of polynomial functions. We're now going to expand our study of polynomial functions to include imaginary or non-real zeros as well. So if you remember, if we look at the entire number system, the complex number system, complex numbers include real numbers and imaginary numbers. So in this section we expand from just the real zeros of the polynomial functions to all of them. So when they say complex, it doesn't necessarily mean that it's imaginary. It just means that it could be imaginary. We're now counting the imaginary zeros. Whereas in the previous section, if we found imaginary zeros, they weren't asking us for those. We didn't include those in our answer. Okay, so in this section, we're going to learn how to find the complex zeros of a polynomial function, so all of them. Okay, the fundamental theorem of algebra. Every complex polynomial function, f of x, of degree n greater than or equal to 1 has at least one complex zero. And then we can get more specific with that. It follows then that every such complex polynomial function, f of x, can be factored into n linear factors. So we know linear, x to the first power. So our polynomial function f of x, we can factor it into some constant, a sub n, and then a product of the factors x minus r1 times x minus r2 times ... continue that pattern all the way down, x minus r sub n, and then a sub n, r1, r2, etc., all the way to rn are complex numbers. So basically, for all of the zeros, we can make linear factors x minus the zero. So for the zeros r1, r2, r sub n, we can make linear factors by taking x minus them, which we know. So then we can say from that every polynomial function f of x of degree n greater than or equal to 1 has exactly n complex zeros. So we said in the previous section that the degree told us the maximum number of real zeros. Well, now we're expanding this to say that that degree actually tells us the exact number of complex zeros. If the number of x-intercepts is less than the degree, then the function will either have repeated zeros, which we can call multiplicity, and or it has imaginary zeros, and we'll see this when we look at some examples. And then finally our conjugate pairs theorem. So if a plus bi, if your complex zero, a plus bi, if you have that zero, then you know that its conjugate pair, a minus bi, is also a zero of f of x. So the imaginary zeros, they come in pairs. So we'll never have just one imaginary zero. They'll always come in pairs. So we'll have like 2 or 4 or 6, etc.